I have this piece of code, I have to analyze and find the time complexity of this one, and this code also for loop is used. But loop is starting from 1 going up to n, that is less than n, and it is being multiplied by 2, I is multiplied by 2 every time. So blindly we cannot say this will execute for n times. We have to analyze this one. Let us see how many times this will execute. It's not n, we don't know how many times. Let us see. I will take the I value, initially this one. The next time is going to be 1 into 2, that's 2. The next time it will be 2 into 2 again, so it will be 2 square. See, every time it's getting multiplied by 2. That's 2 square into 2 again, so this will be 2 power 3. Goes on. How many times? That we don't know. So let us say this will execute for 2 power k times. 2 power k times. Now, we know that this will terminate when I becomes greater than or equal to n. So we assume that when it has reached for some k number of times it has repeated, assume I became greater than or equal to n. And what's our I value? 2 power k. Since I is equals to 2 power k, therefore 2 power k has become greater than or equal to n. Now if I take 2 power k is equals to n, then k is how much? Log n base 2. Yes, this is the time complexity. So the statement will execute for order of log n base 2 times. So from this we can observe that if you have a loop where the counter variable is not incrementing but it's getting multiplied by something, let's say 2 or 3, then it will get log base 2 time. So it will execute for log base 2 times. Now I have an incremental for loop here, the regular loop that we use. Let us analyze that one and then we will analyze once again here the other method I will show you. See here, I is initially 1 and it is incrementing by 1, plus 1, then plus 1, then plus 1, goes on, plus 1, and it will stop and finally it becomes greater than n, so up to n. So how many times it's getting added? So let's say k times, and that is equal to n. So how many times k times? What is that k? It's equal to n. Now let's take this one. I is initially 1, then it is next time into 2, then again into 2, then again into 2, so up to sometimes. So finally it will stop when it becomes greater than or equal to n. Then this is how many times? So this will be, let us say, k times. So what will be the result? This will be 2 power k, that will be equal to n. So k is how much? Log n base 2. So the other way we have analyzed this one, so that is incrementing 1, 1, 1, so k times, so this is multiplying by 2, 2, 2 every time. So k times is getting multiplied. So it's 2 per k, that is equal to n. So k is how many times? K is log n base 2 times. So if you have a loop like this, the value of I is getting multiplied, then it is going to take log n times. So you can take it as a formula. The time complexity taken by this will go down as log n. The statement will be for log n times. When we take log n will give decimal values, float values. So we need to know whether I have to take float or seal of that value. So that's important, means it should be truncated or round up the value. So for that, let us take some example and check it. Suppose n value is 8. Right. Now I value, let us start trace this one by taking a sample value. I is 1 initially, then I is multiplied by 2, so it's 2, 2 is less than 8, 2 is less than 8, then again multiplied by 2, 4, so 4 is less than 8, and it's 8, right? So again multiplied by 2. Now 8 is not less than 8, so it will stop. So total how many times it is repeating? It is repeating for 3 times. The next, if I take the n value as 10, if I write the n value as 10, let us see what happens. I is initially 1, 1 is less than 10, now n value is 10, 1 is less than 10, continue. It's multiplied by 2, so 2 is less than 10, 4, 4 is less than 10, 8, multiplied by 2, it is 8, 8 is also less than 10, then 16, so 16 is I is not less than 10, so it will stop here. So total how many times? 4 times. It's executing for 4 times. If I find log 8 will be 3. How? Log 8 is written as 2 power 3 base 2, and it is written as 3 log 2 base 2, and this is 1, so answer is 3. Now same way, if I find out log 10 base 2, now 10 is not in exact powers of 2, so I will not get the decimal value, integer value, I will get a decimal value, right? So let us take it as example 3.2, I'm assuming that's 3.2. I got 3.2, but if you see the number of times repeated, 4 times, so it should be taken as seal value. So this log should be taken as seal. When you use log sometimes, whether it is seal or float, that is also important. Right. Another piece of code here, let us see how it's going to execute, what will be the time complexity of this one. See here, I is starting from n. The next time I value is n by 2. The next time it's n by 2 square. Then n by 2 cube, so on. How many times? N by 2 power k. We don't know the number of times, so we are assuming it as for k times. And we know that the loop will terminate when I becomes less than 1. So it will continue as long as it greater than or equal to 1. So assume I has become less than 1. So therefore, what is I value? 2 power k is less than 1. So if I equate it, then it's going to be 1. And n is equals to 2 power k. So k is how much? Log n base 2. So again, the time for this one is order of log n base 2. So the time complexity of this piece of code is also log n base 2. So the previous one, in the fifth example, I have shown you that it was multiplying every time and starting from 1. Now this is dividing every time and starting from n. And up to what? Up to 1 it is reaching. So it's order of log n. Next piece of code is the seventh example I am taking here. So here I is starting from 0 and I into I is less than or equal to n. So how many times this will execute? So this will execute as long as I into I is less than n. But it will terminate when I into I is greater than or equal to n. We assume that I into I is I square is equal to n. So what is I? It's root n. So I don't have to k here, I have not used k here, directly using I only have shown you. I into I is less than n, when this is a square, if you send that side, it's a root, so it will execute for root n times. Now next example, here I have 2 for loops, these are independent loops, one after another. Don't mistake it as a nested loop, they are not one inside another. So the time complexity for this one is, this is independent loop, and it is iterating for n times, and it's incremental loop, so it's order of n. And this is also an incremental loop, this is also order of n. So if you combine them and take their time, that's 2 plus 2, so n plus n, that's 2n, and it is order of n. So this is a independent loop, and the time is order of n only, n plus n, that is order of n. It's not n square. Now which one? I have 2 loops here, independent loops. This next loop, I have to find out what is the time taken by this statement. If I observe only this one, then j is taking values from 1, j is less than n, j is incrementing, that's updating by multiplied by 2 every time. So this is going to take log value. Log of what? Log of p. So this is log p. what is the P? If you see the previous loop, here P is incremented. So P is incremented in this loop, so this P will take the value, that number of times this loop is repeating. How many times this loop is repeating? I take the values 1, 1, 2, n, and I assign I into 2. So again, it's log. Log of what? It is log n. So P value will be log n. And this statement will be for log P times. So what is P? P is evaluated here, and it is used here. Right? So this is log of log n. As P is equal to log n, so it is log of log n. So the time complexity is order of log n. Next example, here I have nested for loop. The outer loop is taking I assign 0, I is less than n, and I is incrementing. So this is order of n. As this is the increment loop, so this is order of n. And whatever is there inside will repeat for n times. Next, the inner for loop, this is using j is less than n, and j is every time multiplied by 2, right? So this will take log n time. So this itself will take log n time. And anything inside that also will take log n time. If you remember initially, I have shown you that this takes n plus 1. Now it will not be any useful if you write n plus 1 or don't write it. It makes no difference. Just you can take it as n. Now total how much? 2n log n plus n. So highest term is this one. So this is order of n log n. So the time complexity of this one is order of n log n. Now let us write some pieces of code and see what the time complexities that we have got so far. See if I write a for loop for I assign 0, I is less than n, I plus plus. For this we got the time as order of n. This is an incrementing loop. If this is written as I assign 0, I is less than n, and I assign I plus 2, this is going to be n by 2, that also will take order of n. Then for I assign n, I is greater than 1, I minus minus, this also order of n. So if it is incrementing also order of n, if it is decrementing also order of n, then for I assign 1, I less than n, I assign I multiplied by 2, this is order of log n base 2. So it means for I assign 1, I is less than n, I assign I into 3, this will be order of log n base 3. For I assign n, I is greater than 1, and I assign I by 2, it's order of log n base 2. So now we can take these as formulas. If a loop is incrementing, that is n, or decrementing, it is n. Whether it is incrementing by 1 or 2 or even 10 or even 100 also, it's order of n only, say. Right? N by 2 is also order of n, n by 200 is also order of n. Because we are writing the degree of the polynomial, that is n is the term used there, the variable n is used, so it's order of n. If n square by 2, then we say n square. Right? So this is a summary of the time complexity we have seen. Hi. Already I have prepared a video how to find the time complexity if there is a for loop. Now the question is how to analyze a loop, that is while loop or conditional statements. See, basically in C language there are 3 loops. While and do while there is a difference. Do while will execute minimum 1 time, but for loop and while loop I say that they are same. Whatever you can do using for loop you can do using while loop and vice versa. But before C language, yes, languages used to provide for loop in a different way. Let us see that for loop. For I assign 1 to n, do some statements inside, and this is colon here. This was the syntax in Pascal language. Now this loop says that I should take the values from 1 and to n, right? So always it will increase by 1 at a time. Alright, so if you want to increase I by 2 times, then you should say step 2. Now I will be changing by 2 every time. So I is 1, then it will become 3, then 5, and so on. So it will take I as 1, then 3, then 5, and so on. But anyway, I is incrementing linearly, it is increasing. Alright, so this was the only loops that were available in those days. So that time for loop and while loop were different. Then when you analyze this for loop, already we have seen what is the time taken. If I don't have this steps, let us say 1 only, then this will execute for n time and this will execute for n plus 1 time. This is a common thing. And if you have while loop in this case, then in a language, if you have while loop, then don't know what the condition is. It will repeat as long as the condition is true, and it will stop when the condition is false. So we have to study this loop and find out when it's going to stop and how many times it's going to iterate. Based on that, we have to do analysis. And in this type of code syntax, blindly for loop it's n, no other time except n in this type of syntax, and when the old languages were used. So mostly in algorithms, some books you will find this loop is used. So it is n, blindly n. But while you cannot say n unless you study it thoroughly. And in C language, we have do while, which is same as this while, except that it will execute even if the condition is false. It will execute for 1 time because it is post-tested loop, post-checked loop. First, it will execute the statement inside. Then afterwards, it will check the condition. So if already condition is false, in the beginning only it is false. So this type will execute 1 time, and this will not execute at all. But in old languages, there used to be a loop called repeat, some statement inside, and until some condition. Now these loops were different. Repeat until loops are different. This will repeat as long as the condition is false. And once the condition is true, it will stop. So it is similar to do while. How? Minimum 1 time the statement is executed. But it is different compared to do while. How? Do while will execute as long as condition is true. Repeat until will execute as long as condition is false. It will stop when the condition becomes true. Do this until this happens. So if it happens, you have to stop. So if you take an English sentence statement, repeat until this happens. So if it happens, you have to stop. If it's not happening, you have to go on continue. So that's the difference between them. Now all these three loops, you have to study them, then only you can give the time complexity. Their time complexity can be n, log n, root n, it can be anything. But for loop, we can directly say it's order of n. Now let me write few pieces of code or snippets where I will use while loop. I have written a piece of code using while loop. I have to analyze how many times this will execute. What is the time complexity of this one? I want to know how many times this statement will execute. Initially I is 0. This will take 1 minute of time. and I++, how many times this will repeat? How many times this will repeat? See, I++, it is just incrementing every time. So simply without tracing this one, I can say that this will repeat for n times. How many times this statement will execute? Again, n times only. How many times this will execute? N plus 1 time. How? N times the condition will be true and 1 time the condition is false. So if, for example, n is 10, then this is going to repeat for total 10 times, 0 to 10. It will stop when I becomes 10. And how long this will execute? As long as I is from 0 to 9. So this is n times, right? And that is 1 extra. Then what is the time taken by this piece of code? 3n plus 2 is 3n plus 2. So the function f of n is 3n plus 2 and it is theta of n, or order of n. Now the same piece of code in C language I can write like this. For I assign 0 here, then I is less than n, I is less than n, I plus plus, I plus plus. Now what is the answer for this one? It will be same if I consider each and everything. This will execute for 1 time, this will execute for n plus 1 time, this will execute for n time, and this will execute for n time. Total how many? 3n plus 2. But when I was using for loop, I was saying that let us ignore these two and just take it as n plus 1. So I was saying that it was 2n plus 1. Whatever the function may be, we are not interested in exact formula or exact function. We are interested in the degree of a function. So we say order of n. That's it. Now you can see whatever I can write using while loop, I can write it using for loop also. Now next piece of code here. See, a assign 1 while a is less than b, some statement, and a is multiplied by 2 every time. There is no n here. Then how many times it will repeat? I don't know. This depends on this condition. As long as the condition is true, it will continue. So I don't know how many times it's going to run. Let us trace this one. A is initially 1, right? Then a is becoming a into 2, so that is 1 into 2, so it is becoming 2. The next time again, this is 2, so 2 into 2 again, so this will become 2 square. The next time again, this is 2 square into 2, that is 2 cube. Goes on. How many times this is going to happen? I don't know. Let us assume that somewhere it stops, and at that time, this is going to be 2 power k. So it will repeat for k times, and that's what k I have to find out. I don't know how many times, so I am saying k times. Now I say that it has stopped here, so you should know when it is stopping. It will terminate when a is greater than or equal to b. It will terminate when a is greater than or equal to b. So what I am saying, I has reached till 2 power k. So since I am saying that a is equal to 2 power k now, so this is 2 power k is greater than or equal to b. Let us make it equal. 2 power k is equals to b. So what is k? Log b base 2. So how many times is going to execute? Log b times. Log b times. Log b times. We write the time complexity in the form of log n. We use term n, but we got the answer in b. So let us call b itself as n. So what is the time taken by this algorithm? It is order of log n. That's it. This is how I can analyze. Already I have shown this using for loop. That time I was writing the same thing by using for loop like this. For a assign 1, a is less than b, a assign a into 2. This portion is here. That's all. Already we have seen this. In for loops I have shown you this one. Already we know this one. That time I was not taking a, I will take I, and again here also I, and this I will call it as n, and this I will call it as I. That's it. Basically, this is not proper based on for loop, because for means it should just go on incrementing or it should be decrementing. It should not multiply I, but in case of C language, it's possible you write anything as initialization, any condition you write, anything as updation. So these 3 pieces you can write whatever you like. Just make sure that the loop terminates after some finite number of steps. So that's all. What all you can do using while loop, you can also do it using for loop in C language. And the examples what I have given, in all the examples I have used for loop only. But instead of for loop, just you can reframe them as while loop. Let us take one more example. Again, a loop is there, while loop, and in this while loop, I is starting from n, and I is getting divided by 2 every time. So again, the time will be log n. I made it as a formula already in the previous video, so this will be log n. And the same thing can also be done using for loop. For I assign n, I is greater than 1, I assign I by 2. Some statement inside. So this type of statement already we have analyzed in for loop. The same thing is using while loop, so the time will be same. Now here I have a loop. Let us see how many times this will execute. Condition is k is less than n. And here what is k? K is 1 and k is getting updated by adding I every time, and I is incrementing every time. So I don't know how many times it's going to execute. So let us trace this one. I and k, initially both are 1. So 1 is less than n. We don't know what n is. And what happens? K assign k plus I. So this becomes 1 plus 1, that is 2, and I plus plus I becomes 2. Now assume k is 2, 2 is less than n. Then next k assign k plus I. So 2 plus 2, right? And I becomes 3. The next time, again k let us say it is less than I. So then k assign k plus I. So this is 2 plus 2 plus 3, and I becomes 4. Next time it will be 2 plus 2 plus 3 plus 4, and I becomes 5. So this is going on continuing. So how many times? I don't know how many times. Let us call it as for m times. K already I'm using it here. So 2 plus 2 plus 3 plus 4 plus goes on to m. If I make this as 1, then you can see that is sum of n natural numbers. So this will be m into m plus 1 by 2, roughly, plus 1 extra. Roughly it is this much. Now this is, k value will be this much. It has gone till m. And k value this much, and let us assume it has stopped. So what is the condition? K is less than n, it will continue. When k becomes greater than n or equal to n, it will stop. So I assume that k became greater than or equal to n. So what is k I am saying? I have stopped k at m into m plus 1 by 2, that is greater than or equal to n. This is roughly equal to what? M square is greater than n. So m is what? Root n. Approximately it is root n. So it will repeat for m times. So what is m root n? So the time complexity of this one is order of root n. Same thing I can write using for loop also. For k assign 1, comma I assign 1. 2 initializations. Condition is what? K less than n. Updation is what? I plus plus. And one more updation is there that I will do inside the statement, and k assign k plus I. It's the same thing. How long this is executing? Root n. How long? Root n again. 1, 2, 1, 2. Condition, condition, updation, updation, this updation, and this updation. Everything is as it is. So what I wrote using while can also be written using for. This is a little difficult to read, that is clear and easy to understand. Alright, so already we have seen this type of loop. Now I have written it using while loop. Next, this piece of code is for finding GCD of two numbers, m and n. Now how many times it will repeat? This will repeat for some time until m and n becomes equal, it will be repeating. When they become equal, it will stop. So when they are equal, so that is the GCD value. Either you say m or you say n. How many times it will execute, I don't know. So let me trace. If m is equals to 6 and n is equals to 3 initially, then what happens? N is greater than n. Yes. So m minus n. So this becomes 6 minus 3, that is 3, and this is also 3. That's all. Now they became equal. So it has executed only one time. If I take m and n both as 5, 5, then how many times? They are equal, it will not enter inside, so it will execute 0 times. So it is minimum executing 0 or 1 times. Let's say m is 16 and n is 2. Now how many times this will execute? M and n are not equal, m is greater than n, yes, 16 is greater than 2, enter inside m, assign n minus n. So m becomes how much? 14, and this will be 2 only. Then again m is greater than n only, so again 2 is subtracted, so this becomes 12 and this is 2 only. Again 12 is greater than 2, so this becomes 10 and this is 2 only. And this becomes 8 and 2, 6 and 2, 4, 2, 2, 2. Now it will stop. Now they both became equal, so it will stop. How many times it has executed? 1, 2, 3, 4, 5, 6, 7. 7 times. So almost 16 by 2 times. So it means it will execute for n by 2 times. So I can say it is order of n. So the maximum time taken by this algorithm is order of n. And what is the minimum time taken by this algorithm? It is 1. Means 1 time it is executing. So minimum time is order of 1. Maximum time is order of n. I can write the same thing even using for loop. I'll just convert it into for loop. For nothing initialized and only the condition, then no updation. I can use for loop also. Anyway, this is the GCD, one of the procedure. There are other procedures also, you can find out that. And in this procedure, the time I'm getting it as n by 2, so I wrote it as order of n. So if it's a while loop, then I have to study it and find out. Now same thing in C language can also be written using for loop. So even if it's for loop in C language, you must treat it as while only and study it. Unless and until it is obviously order of n, you have to study it. Yes, I'm taking one example here which will show what happens if is there. Just a random code I have written here. It's not meaningful, it's not doing anything. Algorithm test is taking some parameter n. If n is less than 5, just print n. If n is greater than or equal to 5, then enter in the else part and repeat this loop. So how many times this loop is going to execute? This will execute for n times. And what about this? This will execute for 1 time. That's it. If a algorithm is using some conditional statements, then the conditional statements may decide different amount of time depending on the condition. If the condition is true, then it's going to execute just one statement, so the time is order of 1. And if the condition is false, means it's greater than 5, then it's going to repeat for n times, so it is order of n. So this is best case time and this is worst case time. So I can say that if there is a conditional statement in an algorithm, then it can decide or give different amount of time depending on the condition. So maybe it may become worst case or best case of an algorithm. It's not necessary. It's not necessary. It may. It doesn't mean that if is there, it's not like a formula or rule. If it's there, then definitely it will take that much time. It's not necessary. Now I'll make some change here. Change the condition now. Now this will execute for n times, n greater than 5. Right? Now there is no minimum or maximum. There is no best case or worst case. If n is greater than 5, it will execute. That's all. So as I said that you cannot take it as a rule that if conditional statement if is there, then the time will be different. Alright. So that's all about the loop and the conditional statements, while loop and the conditional statements. This is how they have analyzed. Now next, let us look at the types of time functions that we have got, the time complexities that we have obtained so far. We have got the time complexity as order of 1. So this we call it as constant. If the time complexity of any function, of any algorithm is 2, then it is constant. If it is 5, then also it's constant. If it is 5,000, then also it is constant. So actually, that doesn't mean the value. That is showing that the value is constant type. It's not dependent on size of the input. It's not order of n. N is the size of the input, so it's not dependent on n. Then the next one we got was log n. Log n base 2, base 3, whatever the base of log may be, this is logarithmic. The time complexity is logarithmic. Then order of n we got, so this is linear. The same way, if you have the function f of n is equals to 2n plus 3, then it is order of n. Even if you have f of n is equals to 500n plus 700, then also it's order of n. If you have f of n equal to n by 5000 plus 6, then also it's order of n. See, we are trying to say that the degree, these are all polynomials, the degree of a polynomial is 1, that is n power 1, so we write n. We don't write the degree, we write the term itself, so it's order of n. Then, for some algorithms, we got the time complexity as n square, so this is quadratic. And for some algorithms, we got it as n cube, matrix multiplication, cubic, and this was matrix addition. Then for some algorithms, we may get the time as 2 power n also, so this will be exponential. We haven't seen these type of algorithms, but we may come across later on in coming videos. This is exponential. It may be 2 power n, or it may be 3 power n, or it may be n power n. It may be to the power of anything, so 2 power or 3 power or n power n. So I call this as classes of functions, or the types of time functions, or also classes of functions, or categories, whatever you want, you can name this. Alright, so these are the different type of functions. So we have the class here, that is linear class, or logarithmic class, or quadratic class, or cubic class. So we have the classes over here. Here I have written those classes of functions in the increasing order of their weightage. This means that n is always less than n log n, and that's always less than n square, or log n is always less than root n as well as n as well as, so it's less than all of them. So n power 3 then goes on n power 4, 5 or up to 100 also, that is less than 2 power n. and 2 power n is less than 3 power n. So that's how they are written in the increasing order of their weightage. Now to prove that, I will take few terms from this one, few classes from this one. Let us say log n square 2 power n. Let us try this. If I take n value as 1, log 1 will be 0, and this will be 1, and this will be 2. 2 power 1 is 2. If I take this as 2, then log 2 base 2 is 1, this is 1, and this is 4, and this is also 4. If I take n value as 8, then this is 3, and if I take n value as 4, then this will be 16, and 2 power 4 is also 16, and this is 2. If I take n value as 8, this will be 3, and this will be 64, and this is 2 power 8, that is 256. So you can see that there is a sudden change. See, I have taken 8 here, so this is slower growth and this is a very faster growth in the value. So that's 2 power n. And you can see that, now if you go on putting the values, this is less than this one, and this is less than this one, this is less than this one. But if you observe this, up to here, these two values were equal. And here also these two values were equal, right? And this time it was greater, right? Again, it is greater. So sometimes it was less or greater or equal, whatever it may be. But from this point onwards, we can guarantee that 2 power n will be moving with a faster speed, right? So if I take 9 here, then some log of 9, maybe I will be getting 3.1 something. But here, 81, and this will be 512. 2 power 9 is 512, right? So around 20 values, around 16 or 15 is added here, so that much increase. But that there, you can see that there's a bigger change in the value. It's a double again. Right? So always 2 power n is greater, and above that is greater than that is 3 power n, and the highest is 2 power n power n. So from this we can say that for some values of n, this is smaller than this one, or this is greater than this one. So they are arranged in the order. Alright, so even if you have n power 100, that's also less than 2 power n. You write anything to the power of n power k. K can be anything, the value that you can imagine, you can write on that, and that's going to be less than 2 power n. How come? See, n means don't assume the values of n very small, that is starting from 1 or 2 or 10. Usually n means we imagine it as 10 or 5 like that. No, n can be any number. So n can be 0 to infinity. Right? So for larger values of n, at some point, n power 100 will be smaller than 2 power n. And from that point onwards, 2 power n will be always greater. So there will be some starting value of n for which that will be greater. Look on the graph. For n, suppose this is log n. This line is showing n, and this line is showing n square. So this is log n, and this is n, this is showing n square, and this is showing n cube. Then this will show 2 power n. This represents 2 power n. So initially the value of 2 power n may be smaller, then certainly it will have a higher rate of increase. Right? So this is not for same x and y values. So just n values I have written, and I have drawn some lines here. Alright? So representing this is smaller than this one, so this is smaller than this, so this is greater than this, this is greater. So like that 2 power n is greater. So initially it may be smaller for some values of n, then certainly it may increase. So this inequality is very, very important. This is very important. The arrangement, the order in which they are arranged, that is very important. Hi. The next topic is asymptotic notation, and this is a very important topic in algorithm. Let us understand what this topic is about. So first of all, let me tell you that this topic is coming from mathematics. Functions belongs to mathematics, so this topic also belongs to mathematics. But as for the time complexity, we are using functions in algorithms. That's the reason this is also used. The notations are also used. The notations are used for representing the symbol form of a function, or showing the class of a function. If we have any function, we can show that this function belongs to so and so class. And you already know the comparison of functions also, which function is smaller and which is greater than which one. So we know their order, increasing order also. Now for representing any function in simple communicable form, so that one can easily get the idea about the algorithm. So that's why this is the mostly needed topic for algorithms, because we cannot write a lengthy function every time. We need a simple method for representing the time complexity. What are the notations used? Big O notation. This works as an upper bound of a function. Big omega notation. This works as a lower bound of a function. And theta notation. This works as a average bound of a function. Average bound of a function. Any function you can represent as either upper bound or lower bound or average bound. Now what is useful out of these three? This one is useful. This one is useful. Then why do you have these two? Why do you need upper bound? If you cannot specify the exact place of any function out of these, then you can show the upper bound of that function. Now let me tell you one thing. When you find the time complexity of any algorithm, the time complexity will be one among these. And if it is not among these, it may be a multiple of these. Right? If it is not even multiple of these, then you may not be able to exactly represent theta, then you can go for big O or omega. So you will see through these examples. This is a big O notation. As per the definition says that the function f of n is equals to big O of g of n if and only if there exist positive constants c and n0 such that f of n is less than or equal to c into g of n for all n greater than n0 or n naught. This is the definition. Now what does it mean? Let us understand. Example, if I have a function f of n is equals to 2n plus 3, then 2n plus 3 is less than or equal to something I should write here such that that is greater than or equal to this one. So what I can write? I can write anything that should be greater than or equal to this one. But one thing I have to take care. This function is having two terms, so I should not write multiple terms. I should write only a single term. That single term can have some coefficient. That c means it can have some coefficient. So what I do is I write 10n. Is it greater? Yes, this is greater than this one. If I put 1 here, this is going to be 10. If I put 1 here, this is going to be 5. So 10 is greater than 5. So this is for all n greater than or equal to 1 onwards. Right? So in this is f of n, this is c, and this is g of n. So g of n is what? N. Now therefore I can say f of n, what is that f of n? 2n plus 3 is big O of n. G of n is n. So f of n is big O of n. See, I have written 10n there. So 10n, not what I should write. So students get confused here. 10. whatever you want, you can write there, but make sure that this portion is greater than this one, or this function is greater than this one. So can I write 7 in here also? Yes. So 7 is also true, and 10 is also true, 1000 also is true. Anything you write there, but make sure that this is greater than that one for some starting value of n. Now instead of going through all this, instead of struggling to get the value there, so the simple method is, you can make this as 2n plus, this is just 3, this also you make it as 3n. So this will be 2n plus 3 is less than 5n, and this will be true for all values greater than or equal to 1. If I put 1 there, both the sides will be 5, they are equal. If I put any other greater value of n, then definitely 5n will be greater. So that's it. Again, this is g of n, and this is true. F of n is big O of n. So simple method to get this side function is make all these terms as multiples of n. For the same function, can I write 2n square plus 3n square? And that becomes 2n plus 3 is less than equal to 5n square for all values of n greater than equal to 1. Yes, this is also true. This is also true. Then what is g of n here? This is c and this is g of n. And as we know, that's f of n. So what is g of n we got? N square. So can I say that this function, the same function, can it be big O of n square? Yes, this is also true. This is also true. Whether you say big O of n square, that's also true. As we are writing an upper bound, that is big O, that's upper bound. So both n and n square becomes upper bound of that function. This f of n actually belongs to this class. It belongs to this type of function. This one. It means all those functions which are greater than or equal to this one, including this becomes upper bound. And all these functions, including this one, on this side becomes lower bound. And what this exactly becomes? This becomes average bound. Average bound. That's it. All those functions I can write them as upper bound. So saying for this function, big O of n is also true, big O of n square is also true, f of n is equals to big O of 2 power n is also true. All those are true. But I cannot say f of n is big O of log n. No, this is coming on this side, this is coming on lower bound side. So I cannot say it is big O of log n. This will be wrong. This is wrong. I can say all these things. All these are true. Now the question arises, why do I need to write all those? When it's actually equal to this one. Yes, when you write big O, try to write the closest function. Try to use the closest function. So which is the closest function in this one? This is the closest function. Though, if you write any other higher value function also, it is true, it's not false, but it is not useful. So we prefer writing anything that is closer to that one. Right? So this is about big O notations. Omega notation. As per the definition, the function f of n is omega of g of n if and only if there exist positive constants c and n0 such that f of n is greater than or equal to c into g of n for all n greater than or equal to n0. That's the definition. Compared to big O notation, only the symbol has changed and the symbol has changed. The inequality sign has changed. This was less than or equal to, now it is greater than or equal to. That's the only difference. Now if I take the same example function, f of n is equal to 2n plus 3, then I can write 2n plus 3 is greater than or equal to just 1n. So earlier we saw in big O we were writing every term as n, now you can just write 1n. You can take the help of 1 here. So just 1n for all n greater than or equal to 1. Right? Even maybe 0, it's starting from 0 also. So that's not much important anyway. You can find out from which value it's starting, you can write on that one. So 2n plus 3 is greater than or equal to 1n for all n starting from 0 onwards or 1 onwards. So this is f of n, and this is c, and this is g of n. So therefore, I can say f of n is omega of n. This is true. So can I say here, instead of 1, can I say log n? Yes, this function is greater than log n also. So even I can say f of n is omega of log n. This is also true. This is also true. But I cannot use any value other than this one. So if you remember that this belongs to this class. So I cannot write anything beyond this one. So I cannot say f of n is omega of n square. No, this will be wrong. Because this is becoming an upper bound, this is not a lower bound. So I can write anything from this side. All will be true. Anything you write, that will be true. If you write log of log n or root n or log n, anything you write, that is true. But which one is useful? The nearest one is useful. This one. Because this directly belongs to this class. So this is equal. Right? Greater, or this is less than or equal, I can say. Right? The function is greater than or equal to this one. So this is less than or equal to the function. Alright? So if I write any other smaller value, that may be true, but not useful. Next one is theta notation. As per the definition, the function f of n is theta of g of n if and only if there exist positive constants c1, c2 and n0 or n0 such that c1 into g of n is less than or equal to f of n and that is less than or equal to c2 into g of n. If I take the same example, f of n is equals to 2n plus 3, then 2n plus 3, already we found the lower bound, that was 1 into n, and already we found the upper bound, that was 5 into n. So this is f of n, and this is acting as c1, and this is g of n. This is c2, and this is g of n. So both the sides we have g of n as n and it is same. So then only you can take it. This is g of n, then that is also g of n. Therefore, I can say f of n is theta of n. That's it. This is the average bound of a function, f of n. And this shows that this is exactly equal to this one. Now, when I got this one, I cannot say f of n is theta of n square. I cannot use this. I cannot write any other thing except n. Because if I write n square here, this will be wrong. If I write log n here, but log n will be wrong here. So I cannot use any other thing both the side, except this n can be used on both the sides. Theta notation is average notation. So here I can use only n. I cannot use any other value, and this is mostly recommended whenever you have any function and if you are able to represent present theta notation, that's better. But it's not possible, then you can go for rho or omega. And one more important thing, don't mix this term with best case or worst case of algorithm. Mostly people get confused by mixing this with best case or worst case of algorithm. It's not related to best case or worst case. Mostly people think that rho is used for upper bound, so it is for worst case, omega is for lower bound, so it is for best case. No, you can use any notation for best case, any notation for worst case. I'll explain this point in some other video when I discuss about best case and worst case analysis. So remember that this is not related to best or worst case. It's not related to case analysis. These are just notation for representing bounds of a function. Let us take few examples. F of n, if it is 2n squared plus 3n plus 4. Suppose it's a function. So 2n squared plus 3n plus 4 is less than 2n squared plus 3n squared plus 4n squared. So this 2n squared plus 3n plus 4 is less than or equal to 9n squared. For all n greater than or equal to Some value you can find out from which value is starting and just put one there. Now let's take few examples. F of n, if it is 2n squared plus 3n plus 4. Suppose this is a function. So 2n squared plus 3n plus 4 is less than 2n squared plus 3n squared plus 4n squared. So this 2n squared plus 3n plus 4 is less than equal to 9n squared. For all n greater than equal to some value you can find out from which value is starting and just put one there. So this is greater than equal to this one. So this is c and this is g of n. So it is f of n is big O of g of n. So g of n is what? N squared. F of n is big O of n squared. Now for the same function, I can say 2n squared plus 3n plus 4 is greater than equal to 1 into n squared. So it is omega of n squared. So even I can write omega of n squared, I made it as 1 into n squared. Now same thing, 2n squared plus 3n plus 4 is lying in between 1n squared and 9n squared. So this is theta of n squared on both sides. Next, if f of n is n squared log n plus n, then n squared log n plus n is less than equal to 10 n squared log n. I just wrote some value greater than there. And here it is less than equal to 1 n squared log n. So both side I got n squared log n and n squared log n, and this is smaller, this is greater than this one, and this is smaller than this one. So both side I got n squared log n and n squared log n. So this is big O of n squared log n and omega of n squared log n, as well as this is theta of n squared log n. So all three I have written them together here. Now if you observe in our this orders, we have not written n squared log n. But if I write n squared log n comes in between n squared and n cube. N squared log n is greater than n squared but less than n cube. So there's a combination of n squared and log n, and for this also you can specify a class here in between those two. You can mention a class. Next, if a function is n factorial, then let us see. N factorial is nothing but n into n minus 1 into n minus 2 into goes on to 3 into 2 into 1. So if I write in reverse, then 1 into 2 into 3 goes on to n. Now this is greater than less than equal to what? See, as a practice what we were doing, everything we were making it as n. So here also I'll make it as n into n into n into goes on to n. And this is less than equal to what? So as a practice we'll make everything as 1 into 1 into 1 into goes on to 1. So this side I get 1, and this is n factorial, and this is n power n. Now for this one, for n factorial, I don't have any smaller value here, and I have to take it as 1. And if I take larger value, it is n power n. Upper bound is n power n. And both the side, I'm not getting same thing. I'm not getting same thing. If I get same thing, then I can take it as theta. So what I can write big O of n power n and omega of 1. So the lower bound for n factorial is 1. Upper bound for n factorial is n power n. Right? So here, we cannot find the type bond or average bond or theta for n factorial. So if you try to put n factorial here, class is not there for n factorial, but if you try to put it there, then for the smaller values of n, it will be nearer to this one, and for the larger values of n, it will be increasing and going up to n power n. So you cannot fix a particular place for n factorial. You cannot say that n factorial is always greater than n power 10 and less than n power 11. You cannot say that. You cannot find a place for it. You cannot find a place for it. Right? So it's greater than equal to 1, but less than equal to n power n. So upper bound is n power n, and the lower bound is 1. So this is the function for which you cannot find the theta. So now upper bound and lower bound are useful. As I already told that when you cannot mention theta bound for any function, then we go for upper bound or lower bound. So yes, here we have taken upper bound and lower bound of a function. Let's take log n factorial. So for log n factorial, if I write log of 1 into 2 into 3 and so on to n, then this is less than or equal to log of, as a practice we'll make everything as n. So n into so on to n. And it is less than log 1 into so on to 1. So this side will be 0, but we write 1, and this is log of n factorial, and this is less than equal to, this is log of n raised to n, and that will be written as n log n. That power comes on this side and this is n log n. So now you can see that for n log n factorial also, upper bound is log n power n, and the lower bound is 1, and there is no type bound for this function. So the factorial function, we cannot define the type bound. So we go for upper bound as n log n, and lower bound as 1. So there is no type bound. So now you have understood when you use big O notation, when you use omega, and always theta is preferable. If you are able to find theta for any function, that's better, because that's a type bound. And if you're using upper bound, we also try to use a type bound. Don't give a very far away value, a larger value. And if you're using lower bound, don't give any smaller value. Try to give a nearest value for a function. Suppose your function is n squared, so try to give it n squared only. Though writing n log n or n or root n is also correct, true, but not meaningful, but not useful. If I ask you that I want to buy a mobile phone for my requirement, what could be the better price? So any price for a mobile phone that's available in the market. So suppose you have some idea about the mobile phone, and you said that you can buy a mobile phone for around 20,000. So you are giving me nearest figures. If I say, if you don't know the nearest figures, and if I ask you, tell me something minimum, so you are saying that 18,000, 19,000, or maximum, you can say 21,000, 24,000 like that, so you are nearer only. But if you say minimum means 2,000, 3,000, so your answer is correct. I can get some mobile phone in 2,000 also, smartphone also, but that will not be a suitable one for me. But your answer is right, but it's not useful. And if I ask maximum, so you say 1 lakh, 2 lakh, so even for 1 lakh, 2 lakh, mobile phones are also available. Answer is correct, but not meaningful for me. So same way, when you have any function, n square, then you can say n square, that is the answer, perfect answer, so giving theta is the right one. But if you're writing omega, so I'm not sure whether you are giving me nearest or not. That's the problem with big O. It may be nearest one, it may be bigger than that one also, but theta guarantees that you have given the exact figure, exact notation, exact time complexity. When you're using omega, then also it means that you may be giving a lower value, may or may not be nearest one. So that's why big O or omega are used when you're not sure about the exact one. Right? That's the meaning it is. So that is much suitable for n factorial and log n factorial, but you can use them for any purpose. It's not a rule that you must not use, you must use theta only. You can use any notation. So when you're using omega, means maybe minimum this one, and maybe it is more than this. the time may be more than this also. That's the meaning. Theta means exactly this much time. So hope you have understood this topic. This is a very, very important topic. Now in coming video, that's next video, you can find the properties of asymptotic notations. You can watch that video. Hi, let us see some properties of asymptotic notations. General property. If f of n is big O of g of n, then a into f of n is also big O of g of n. This means, example, f of n is 2n squared plus 5, for example. And if I say this is big O of n squared, then 7 into f of n will be 7 into 2n squared plus 5, 14n squared plus 35. When 2n squared plus 5 was big O of n squared, then 14n squared plus 35 is also big O of n squared. Actually here we have written the degree of this one, and here also we can write on the same degree, so this is order of n squared. So this means that if already for any function you know the big O function, then if you multiply that function f of n with anything, then also big O will be the same. So this a is a constant, so constant value. So this is true for big O, and even it will be true for omega also. If this is omega, then also this is omega. And it is true for theta also. So the same property applies for all three notations. Reflexive property. If f of n is given, then f of n is big O of f of n. It means, example, f of n is n squared. So this is big O of n squared, that is f of n only. So a function is the upper bound of itself. Yes, it is true. Upper bound is any function greater than or equal to. Greater than or equal to. So that same function is the upper bound of itself. And similarly, this is for upper bound only I have shown you. Now if it is lower bound, then any function that is smaller or equal to forms a lower bound of a function. Right? So if any function is given, let us say, just I'm writing one term, okay, n squared, then it is big O of n squared only. So it's big O of itself. Yes, this is true. F of n is big O of f of n. And here one more thing, when I'm writing here is represented using equal to symbol also. Next is transitive property. If you have f of n is big O of g of n and g of n is big O of h of n, then f of n is big O of h of n. Yes, this is true. Let us take example. I will try to write upper bounds. F of n is suppose n, and g of n is n squared, and h of n is n cubed. If these are the functions, then n is big O of n squared, and n squared is big O of n cubed. Then n is big O of n cubed. See, this is f of n, g of n, g of n, h of n. So here, f of n and h of n. So when g of n is an upper bound for f and h is an upper bound for g, then h is also acting as an upper bound for f also. It's a simple thing. So transitive property satisfies on asymptotic notation for all three notations. I am showing only one notation, that is big O. That is true for omega and theta also. Now symmetric property. If f of n is theta of g of n, then g of n is theta of f of n. Now symmetric property is true only for theta notation. Example, f of n is n squared and g of n is also n squared. Then f of n is theta of g of n, that is n squared, and g of n, that is theta of n squared, that is f of n. When both the functions are same, then they are symmetric. One is theta of another, and that second one is the theta of first one. So both, right? First one is theta of second one is the theta of first one. So this is true only in case of theta notation. This is transpose symmetric. This is true for big O and omega notations. If f of n is big O of g of n, then g of n is omega of f of n. Example, let us take, if f of n is n and g of n is n squared, then n is upper bound n squared and n squared is lower bound n. So for n squared, n is lower bound, for n squared is upper bound. So these two are function n and n squared. So one is upper bound for another and vice versa. Next one is the lower bound for another. Right? So this is true for upper bound and lower bound. So first I have taken upper bound, so then lower bound, you change it. This is lower bound, then that is upper bound. So if one function is forming an upper bound for this one, then this function becomes a lower bound for that function. Now there are a few more things. If f of n is big O of g of n and f of n is omega of g of n. So this means that there is one function g of n which is acting as an upper bound for function f as well as lower bound for function f. Then definitely, so if function f of n is here, then f of n is here and this is acting as a lower bound as well as upper bound. So when you have g of n on both the sides, same g of n both the sides, then therefore f of n is theta of g of n. Yes, when the same function is both upper bound as well as lower bound, it's actually equal. That's how it is coming in upper bound as well as coming in lower bound. So in upper bound we take equal or greater. Lower bound also equal or greater. If something is appearing in both ways, it is equal. So that is theta 1. Let's let us take one problem. If f of n is big O of g of n and d of n is big O of e of n. There is one function f of n, upper bound is g of n. There is function d of n, its upper bound is d of n. Then f of n plus d of n. What will be the answer? Let us take example and check. Example, f of n is n and d of n is n square. Then for this one, we go of n, and for this one, we go of n square. And if I write f of n plus d of n, then what this will be? N plus n square. Then what will be the answer? This is big O of what? Big O of what? The greater term is n square, so it will be n square. Now, as per my example, here I have taken this as n and this as n square, so n square became the answer. If suppose this was n square and this was n, then this n square will become answer. If f of n is n square, if this is square and this is n, then again the answer is same. So it means the answer will be the maximum of these two terms. Whichever is greater, that will be the answer. So yes, then f of n plus d of n is big O of max of g of n comma e of n. G of n comma e of n. So for f of n, if you have a big O, for d of n also if you have a big O, if you add these two, then which one will be the answer? Next, if f of n is big O of g of n and d of n is big O of e of n, then f of n into d of n, what will be the answer? They are multiplied. So directly I will write, suppose this is n and this is n square, then product will give you n cube. So yes, this is big O of product of this one. So product of these notations, g of n into e of n. This will be equal to big O of g of n into e of n. A comparison of two functions. The function may be time functions or they may be a space functions. So functions, mathematical functions. If suppose I have one function that is n square and another function is n cube, I want to compare them to know which one is bigger and which one is smaller. So which becomes an upper bound and which becomes a lower bound. So for comparing these two, I don't have to check anything. Directly I know that this is smaller and this is greater. But if at all I have to check them, I have to prove, then how I can do? One method is I can sample some values. For example, if I take n as 2, then this is 2 square, right? So it is 4, and this is 2 cube, this is 8. So 4 is smaller than 8, so it is greater. If I take it as 3, then 3 square is 9, and this is 3 cube is 27. So yes, 27 is greater than 9. If I take 4, this is 4 square, it is 16, and this is 4 cube, this is 64. So I have sampled 3 values, that is enough for me to observe that this is always greater than this one. So yes, this is smaller than this one. This is one method of checking whether functions are compared. This is one method of comparing two functions to find out which one is smaller or greater or are they equal. Second method is apply log on both sides. Apply log on both sides. Log n square, log n cube. Then this becomes 2 log n and this becomes 3 log n. Now this is log n, this is log n, they are same only, but this is 2 times, that is 3 times, and definitely this is less than that one. So second method is apply log on both the sides to find out which one is smaller and which one is greater. So if you have some complex functions, then this is useful. This is a known function only, so I am taking a known thing to make you understand what is the method of checking them. So 2 log n, so I should check exact values. 2 log n is less than 3 log n. So for applying logs, you should know some formulas for log. So let me write some formulas here. Log a into b is log a plus log b. Log a divided by b is log a minus log b. Log a to the power of b is b log a. If you have any power here, that will come this side, it will become coefficient. A power log b base c is b power log a base c. Right? So this log value can come as a base here, if it is in power. And a power b is equals to n. Then b is equals to log n base a. These formulas must be helpful for solving log problems. So now the objective is to compare functions. So I will write few functions and let us compare them and find out which one is greater and which one is smaller. Here I have 2 functions. Let us find out which is greater. Compare them. So f of n is n square log n, g of n is n log n whole to the power of 10. So power of 10 is greater. So it looks as if that is greater than this one. We know n square is greater. So now I will confuse. So if you are able to judge which one is greater, right? If you are able to judge, then no need to do anything. If you are able to judge it perfectly, then let us compare and find out by applying log. Apply log. So this is log n square log n, and this is log n log n. This is power 10. You open this one. This is log n square plus log of log n. As we know, log a into b is log a plus log b. So log a plus log b. Now this side it will be log n plus log of log n whole to the power of 10. We have used first formula. Now using the third formula there, this becomes 2 log n plus log of log n. And this is log n plus 10 is in power. So 10 log of log n. Now check this. This is the bigger term, this is the bigger term on that side. Now if you check 2 bigger terms, this is 2 log n and that is just log n. So definitely 2 log n is greater than this one. Now that is a 10 and log of log n and it's just log of log n. So that is a smaller value, log of log n is smaller value. You can take it as 2 rupees some paisa and 1 rupee some paisa. So paisa is smaller than rupees, right? So this is greater. So this function is greater than that one. So this is greater than that one. Second example. F of n is 3 n power root n and g of n is 2 power root n log n. Let us compare. So for comparing, I'll first write it as it is 3 n power root n and this is 2 and this is log n root n log n. So if you apply this third formula, then this can also be written as n power root n. And this is base 2 only, log base 2, here is base 2, it's always, by default, always it is base 2. So it is 2 power log n power n, right, n power n. Now, by using the fourth formula, what I can do is, this I can interchange with this one. So this will be 3n power root n, and that n power root n comes here, and whole to the power of log, this 2 goes there, so 2 base 2. Log 2 base 2 is 1, so it is power 1. So what's the answer? 3n root n, and this is n power root n. Now I have two functions. So I did not apply log without applying log. I have not applied log on both the sides, but I have used the formulas of log for solving them. Even if you apply log also, you can get something. So now what do you see? 3 n power root n, n power root n. So if you see the term, they are same. This is just a coefficient. This is just a coefficient. It is just like 2n square and n square. Who is greater? They are equal. They are equal. This coefficient is ignorable, right? Asymptotically, they are equal. Value-wise, this is greater. Order of n if you write, big O of n square if you write, big O of n square, big O of n square. Asymptotically, they are equal, but the value-wise, this is greater than that one. So if you want a asymptotic answer, then both are equal. Both functions are equal. Now these two functions, let's compare which one is greater. So for this, I will apply log on both sides. So this is log of n power log n, and this is log of 2 power root n. Now this power comes out by applying third formula. So this becomes log n into log n. So that power came this side, so that's log n, and now that is log n. And this power comes this side, so root n log 2 base 2. This is 1. Now what is this? Log square n, and this is root n. Now which one is greater? If you are unable to check it, still you can apply log. Directly write the answer. If I apply log, then this will become 2 log of log n. And this is n power 1 by 2, right? So 1 by 2 log n. Now tell me, which one is smaller? Log of log n is smaller than log n. Yes, this is smaller than that one. You apply log for one time. If you are unable to judge it, then you can apply log again and you can judge it. So here the thing is, we have to judge which one is smaller, which one is greater. So for making it easy, we are applying log. There is no rule, there is no formula, right? Just apply logs so that you can reduce it and see, and you can easily compare them. So here we one time applying, you are unable to do it. So we did it again. Again, confusion is there. Log square n may be greater than just root n because it's square. So just apply log one more time. So you got log of log n, and that is just one log n. So log n is greater than log of log n. Now let's see who is greater. Two functions. Apply log. Log n into log of 2 base 2. This is 1. And this is root n log n. So what's the answer here? Just log n, and this is root n log n. This is greater. So this is smaller. F of n is 2n, g of n is 3n. Which is smaller, which is greater? Both are equal. Both are equal. This 2 is ignorable, 3 is ignorable when you take it asymptotically. Big O of n, or theta of n, or theta of n. Both are same. Both are equal. Both these functions are equal. Now which function is greater? This looks smaller, this looks greater. Let's apply log. Log 2 power n, log 2 power 2n. So this n comes this side, log 2 base 2, this is 1. And 2n comes this side, log 2 base 2, this is 1. Now which is greater? Now don't say they are equal. Don't say they are equal. We have applied log. Then we are comparing them. Now I cannot say ignore that too. Directly in the functions you can do that. Now for comparison purpose you already applied log, so you cannot strike away the coefficient. So this is 2n, that is greater, and this is smaller. So yes, this function is smaller, that function is greater. You can clearly see from here only. Now I have taken this example to make you understand. After applying log, don't cut off coefficients. Don't cut off them. Right. In one of the examples I did that, but that time I did not apply log. Now after applying log I have changed the functions. Now if I cut off coefficient, it will be different answer. It will be wrong answer. Directly from the functions you can cut off coefficients. So applying log, this 2n is greater than n, so that is greater. Actually this is 4 power n, this is 4 power n, and this is greater than this one. For example, let's compare two functions g1 and g2, which one is greater? Now here, it's not a single expression, here is n cube or n square. So for n value less than 100, it is n cube. After that, it is n square, so it's reducing. And this is n square up to 10,000, after that, this is n cube. If I take n values, let us say this is 100, and this is n, and this is 10,000. Now, on this side, who is greater? This side, less than 100, g1 is greater. And from 100 to 10,000, who is greater? Because the figures are there, so I have used this on the bar. Now, from 100 to 10,000, who is greater? See, from 100 onwards, this is just n square. This is n square. And below 10,000 also, this is also n square. So this is also n square. So both are n square. So g1 is equal to g2. Here, g1 was greater than g2. But beyond 10,000, so 10,000 is n square only. After 10,000, this is n cube. So g2 is greater than g1. So this is still there. This is infinity. Now, who is greater? Which function is greater? G1 or g2? G2 is greater. Always. From what value of n? From 10,000 onwards, it's always greater. Before 10,000, they were changing their sides. Sometimes this was greater or they were equal. But from that point onwards, 10,000 onwards, always g2 is greater. So g2 is greater than g1. G2 is greater than g1. So remember this. So whenever you say some function is greater than another function, you don't have to take the small values of n. It can be from very large values of n also. But from that point, it is always greater, then we consider that function as greater. But we don't just check into smaller values and decide. For all values of n, we decide. It's up to infinity. So from 10,000 to infinity, there is no limit. There is no limit. So g2 is always greater than g1. Here some asymptotic notations are given and comparisons there. So we have to find out whether these statements are true or false. Let us check. This is n plus k whole power m, and if you open this binomial, right, two terms are there. So if you open this, it will be n power m. That is going to be a highest term. It is just like, for example, n plus 3 whole square. Then what's the highest term you get there? N square is the highest term. So if m is there as a power, so n power m is the highest term. So we can write this as theta of n square. Yes, it is exactly theta of n square. So this is theta of n power m. Yes, correct. This is correct. Then what about this one? 2 power n plus 1. So this is 2 into 2 power n. 2 into 2 power n. Coefficient is ignorable, and it is theta of 2 power n also, big O also, omega also. Anything you can write. So this is also correct. Big O is correct. Then let us take this one. 2 raised to 2n and this is 2 raised to n. This is 4 power n and that is 2 power n. 4 power n is greater than 2 power n. 2 power n cannot be an upper bound for this one. Wrong. So it should be big O of 4 power n, not 2 power n. This is wrong. The next, this one. This is the root of log n. This is log of log n. Which one is greater? You apply log on both sides and check it. If you apply log, you get what? 1 by 2 log of log n. There, log of n. Still more smaller. So that cannot be an upper bound. This is greater value. That's a smaller value. Smaller value cannot be an upper bound. Okay, this one, if I apply log on both sides, so this will be log n into log n. So that is log square n, and that is just n. So that n is greater. So yes, this is big O. This is big O. Right? So this is correct. So that's it. I have solved few problems using asymptotic notation so that you get the idea of what should be an approach for solving them, and you have some examples. These are the examples. Already I have taken the example. These are from some exams, competitive exams. So if you get any type of question now, you will be able to solve it. If you have practiced this little bit, then you can solve any type of questions on asymptotic notation. So here we end first chapter of algorithms. Like if you take any textbook, then or any university syllabus, the first chapter is about the algorithm, their analysis, and the asymptotic notation. So we have finished this. So in the next videos, you will find the second chapter onwards. That is, we will look at the strategies. That is divide and conquer and greedy method. These are strategies we will start. In this video, we will learn about best, worst, and average case analysis of algorithm. So for example, I will be taking two algorithms, that is linear search and binary search tree. I take two examples, linear search and binary search tree. So first, commonly we use examples on linear search. This is common thing. I will take binary search tree also, and I'll show you the case analysis on binary search tree also. So we'll learn about best case and best case time, worst case and worst case time, and minimum time in worst case, maximum time in worst case, and average case. So you'll come to know all these things. So in this video, you are going to learn these things. The first one is linear search. Linear search. Linear search. If a set of list of elements are given, then when we are searching for any element in that list, then we have different search methods available like linear search and binary search. Let us see how linear search works. Here I have a list of 10 elements, and in this I want to search for some key element. Let us say I want to search for key element 7. What is the method for searching for a key element? For looking for a key element, the linear search will start scanning the list from left hand side by checking each element at a time. So it will start checking whether this is 7, no, go to the next element, is it 7, no, is it 7, is it 7, so it will go on checking all the elements until either it finds an element. Yes, the element is found. So here is an element. So totally in how many comparisons we'll get an element? That is in 6 comparisons we get an element. Suppose I am searching for a key element 20. Then let us start linear search. 20, it will check for the first element, no, it's not present, the next one, next one, next one, next one. It will check all the elements and it finds that 20 is not present in the list. So when we search in a list, the search may be either successful or it may be unsuccessful. So for 7, it was successful and we found it at index 5, and 20 is not found when we have checked the entire list. So this is how linear search works. Now let's understand what is best case and what is best case time, what is worst case, what is worst case. This time we will find out in this linear search algorithm. First, let us see what is best case. Best case. In case if you are searching for a key element which is present at first index, then it is best case. In case you may be searching for any element from the list, but if you are searching for a key element which is present at index, first index, the very beginning index, then that is best case. Searching key element present at first index. This is best case. Then what the time it will take if I am searching for the first key element? Here in my example, 8 is the first key element. If I am searching for 8, then it will take constant time. Best case time is constant. I can write it as order of 1. So best case time is for n elements is order of 1. Best case time for n elements is order of 1. So here I write b of n is order of 1. Now big O omega, what's that? We will see afterwards. So first I have written that function. Now worst case of an algorithm, linear search algorithm. What's the worst case? When the algorithm will take maximum time. If I am searching for the key which is at the last index. Searching a key at last index. In my example, 18 is the key which is present at last index. So that is the worst case. What's the time taken for searching that key element? So I have to check for all the n elements, then I can reach there. Now what is the time taken in this worst case? Worst case time is n. So worst case for n elements is n, and that is order of n. So here I write worst case for n elements is order of n. So now I have best case as well as worst case times given for linear search. Now average case time. Average case is defined by all possible case time divided by number of cases. So for average case, you have to find out all possible cases and the time taken in each possible case and then divided by number of cases. So this type of analysis is very difficult. It may not be possible on every algorithm. So rarely we do it. And mostly for average case, the time that we get will be similar to worst case. So that's why we prefer finding worst case time for algorithms. Average case analysis may not be possible always. Let us check for linear search what are the cases. So let me tell you just, in case if you're searching for a key present on first index, in case if you're searching for a key present at second index, or in case third index, in case fourth index, in case nth index. So these are all cases. So in case if you're searching for a key present at first index, then average time for this one, it is 1. If I'm searching for a key present at second index, it will take 2 comparisons, and third index 3 comparisons, then so on. Last index n comparison. Total how many cases are there? N cases are there. So what is this equal to? This is n into n plus 1 by 2 and divided by n. This is cancelled, and this is n plus 1 by 2. So average case time for n elements is n plus 1 by 2. All these cases and the time complexities we are finding based on number of comparisons. How many comparisons are required for finding an element? Right? So now you have best case and its time, and the worst case and its time, and the average case. So in average case, I consider all possible cases. N elements are there, n possible cases. You may be searching for first element, second element, or third element, any element. So for each I have taken the time and the number of cases by n. So this is n plus 1 by 2. Now let us apply asymptotic notations on this one. See, I have told you in one video, in asymptotic notation, that cases are nowhere related to notations. Notations are for the functions. Cases are just the type of analysis done on algorithm. Let us see how we can apply notations. See, I have best case time as 1. Can I write this as best case is big O of n? So big O of 1? Yes. I can write big O of 1. Can I write it as omega of 1? Yes. Can I write it as theta of 1? Yes. See, what is the function? Function is one constant. So when you have a function constant, this belongs to constant class. So when it directly belongs to constant class, I can use theta of 1. And even I can use upper bound and lower bound also. Right? This we have already studied asymptotic notation. So any function greater than or equal to comes as upper bound, less than or equal to comes as lower bound, and exactly same function, that is theta. So this is theta. Now worst case, the time is n. This belongs to class that is linear. Function is linear. Can I write this as worst case time is big O of n? Yes. Worst case of n is omega of n. Yes, I can write. Worst case of n is theta of n. Yes. I can use any of these notations. There is no fixed notation to show that this is best case, this is worst case. Best case can be written using any notation, and the worst case can also be written using any notation. Right? Don't take it wrong. Big O is for worst case or omega is for best case. No, it's wrong. You can use theta also for best case or worst case. You can use big O for any cases. And even for average case, I have a function n plus 1 by 2. This belongs to which class? It belongs to linear class n. So even that I can write it as big O, omega, or theta. Right? So don't mix up with the cases. That's already I have told you. I have proved this one. Right? When you have a function, for a function you can use big O also, omega also, theta also. All are true. All are correct. Right? Mostly people confuse that this worst case should be big O. This is upper bound, maximum, upper bound. Right? Lower bound, so omega. No, nothing like that. You can use any notation. Now next example is binary search tree. Here I have a binary search tree. I hope that you already know binary search tree. The purpose of binary search tree is useful for searching. The elements are organized such that for every node, all the elements smaller are on the left hand side, all the greater elements on the right hand side. So for searching, if you are searching for smaller element, we go on left side, or greater element, we go on right side. Suppose I am searching for 15, let me show you the working. If I am searching for 15, I'll start from 20. Is it 15? No. 15 is smaller than this one, so go to the left hand side. Is it 15? No. 15 is greater than this one, so go on right hand side. Yes, 15 is found. So what is the time taken for searching? Total how many comparisons I have done? Only 3 comparisons I have done. So the time taken is 3. So actually that is equal to the height of a tree. So what is the height? We usually call it as log n. Like log n is the height. So around 7 elements I have, it's 8 elements. So log 8 is 3. So 3 comparisons are required. So the height of a tree is log n. So the time taken is log n for 15. Now let us understand what is best case and what is the best case time, worst case and worst case time. Best case is Best case is if I am searching for the element which is present in the root. Best case, searching root element. In short, I am writing. Means I am searching for the key element which is present in the root. So how much time it will take for searching for that particular element? Just constant time. If I am searching for 20, just check it in the root. Yes, the element is found. So the best case time is Bn is 1. Bn is 1. Then what is worst case? Worst case. Worst case is searching for the element which is present in the leaf. Searching for leaf element. So what are the leaf elements in my example? 5, 15, 25 and 40. If I am searching any one of those elements, then the time will be maximum. That is worst case. So what is worst case time? Worst case time depends on the height of a binary search tree. What is the height? Log n. So the worst case is log n. Worst case is log n. Right? Now, we'll not go on the average case. Now, this is a binary search tree. For the same elements, I can have a binary search tree like this. In the root I have 40, and on the left child I have 30, and on its left child 25, and on its left child 20, and its left child is 15 and 10 and 5. This is also a binary search tree. This is a left skewed binary search tree. This is height balanced binary search tree. By using 7 elements, this is the minimum height that I can have, this is the maximum height that I have. Now, what is the best case in this binary search tree? Best case is same. For binary search tree, best case is same, searching for a root, that one. Then what is the worst case? Searching for a leaf. So who is the leaf? Only one element. Searching for this one is worst case. But what is the time taken? Depends on the height of a tree. And here also it was dependent on the height of a tree. And the height was log n. And here the height is n. Height is n. So it means that in worst case, minimum worst case time is how much? Log n. And maximum worst case time is how much? N. So I repeat the point once again. See, what is the worst case for binary search tree? Searching for an element present in the leaf. Searching for an element present in the leaf. That is worst case. Then what is the worst case time? It depends on the height of a tree. Leaf element will be at the last level, so that depends on the height of a tree. So what could be the height of a binary search tree? The height of a binary search tree can be minimum as log n and maximum as n. So minimum worst case time, maximum worst case time. Usually this type of questions we find in some competitive exams. So worst case means we know it is maximum, how it can be minimum. So it depends on the type of data structure or type of an algorithm. So I have chosen a binary search tree in which we get minimum worst case time as well as maximum worst case time. So minimum worst case time is log n, maximum worst case time is n, because the worst case time depends on the height of a tree. I should not write log n here, I should write height of a binary search tree, h. Then what h? That h can be as minimum as log n, as maximum as n. That's it. So these are the best and worst case analysis for binary search tree. Now this best case, worst case, we can write using any notation, just like how I have shown in linear search. I can use big O, omega, or theta, any notation. So the things that we study here is that how to find best case and worst case and average case, and what notation should be used. We got the answer for it. And sometimes minimum time in worst case, maximum time in worst case means what? That also I have explained you. This cannot be possible on every algorithm or data structure. In some situations it is possible. So this can be raised as a question. What will be the minimum time? What will be the maximum time? That's all for this video. Thank you for watching. The topic is disjoint sets.